So in this video here, I'm going to be explaining domain, range, function, and vertical line tests. So domain and range, you guys have probably heard before. They are representing x and y values on a graph. But specifically, domain is a set of points, and they're typically known to be the independent variable. And so again, they are the x values that are represented. And the range is known to be the dependent variables. Or the y values. Okay, so what does it mean to be a function? Well, it has to do with the mapping of the domain to the range. So let me write this in words here. So it's a relation that maps each element of the domain to exactly one element of the range. And I am going to underline it, the part where it says one element of the range. So this means that for any x values, it only has one y value that it connects with. So in this case, if x equals 2 equals also y when it's, so let's say you have your x's and your y's. So if x equals 2 equals 1 for y, then it can't ever be 2 is also equal to 3, if that makes sense. So that's what we mean by whether if something is a function. So you wouldn't want x to have a repeated y value, is what it's getting at. So there are two ways you can check if something is a function. One way is the vertical line test, which I kind of showed in the first video before this. The second way to show is if the x values can't or don't repeat. So I have several examples to show you where these tests can be used. So let's start with the first example here. So in our first example, it's asking, is the relation a function? And so here you kind of have a mapping already, and we can assume that this side here is x's and the other side is y's, since these are usually your inputs and looks like that is your output based off the arrows. So in this case, we want to know if it's a function, but also the domain and range. So let's just start there. Domains are typically your x values, range are your y values. So in this case, these are all my x values. So I'm going to write that down. I have a -2, a -1, a 0, a 1, and a 2. It looks like none of my x values repeated, right? So it's looking good so far. These are my y values, so that is my range. So let's write that down underneath. So I have a 5, a 6, a 7, and an 8. And so because I noticed that all the x values are all unique, meaning there's no repeats, and they connect to a y value. Doesn't matter if they connect to the same y values, but in this case, this is a 0, this is a 1, okay? They're different numbers. So yes, this is definitely a function because none of the x's were repeated. So this is good. Now this one here, these are coordinates, so you guys know that this is your x, this is your y. So again, we're going to do the same thing. We're going to collect all the x's because that's our domain. So we have a 1, a 4, a -1. Wait a minute, another 4? There are 2 4s here. So we need to check the y values now, because if these 4s have different y values, then it's not good. It's not a function. So if the y values, looking at them, that's a 3, that's a 5, 7, 7. We have a 3, 5, 7, 7. Okay, so we also have a repeated y value, but we don't really care about the y values here. Let's take a look at these two functions. Or not two functions, these two coordinates. So these two coordinates both had a 4. So we can't have repeated x values, and their y values are different. So this is definitely not a function. Oops, where's my blue pen? Not a function. And this has to do with that the x values repeated, or that these two x values repeated and also didn't have the same y values. I mean, it would be another situation if this was 4, 5 and they just happened to say another 4, 5 here, then you can say it's a function, but these are two completely different coordinates. So in this case, it's definitely not a function. And let me show you why. So let me graph this for a sec, and you're going to see how it fails the vertical line test. So putting some coordinates on here, it's 1, 2, 3, 4, 5, 6, 7. Yeah, 1, 2, 3, 4. When I plot these graphs here, I have it at 1, 3, which would be right here, 4, 5, which would be right around here, and then I have one at -1, so that's going to be over here at -1, and it's like up 7, so like right here. And then I have another one that is 4, 7, so 4 up 7. So that would be like right on top of it. And so if I were to draw the curve, this would connect here, here, and then up there. Notice how, like, if I were to do a vertical line test, all of these would pass until I get to x equals 4. It fails here because it hits it at two places on the graph, and that's not good. So if you were to draw a vertical line and it hits two places on the graph, well, then that is not a function, because that's telling me that that x value, x equals 4, has two places that it hits, or two y values that it hits, and that makes it not a function, because a function is a mapping of one x value to one y value, and that's what it means to be a function. Hopefully that explanation helped a little bit, but let's move on to another practice one. So again, I am going to be looking at C and determining if it's a function or not, but let's first get the domain and range. So you have input and output here, but like I said before, inputs are usually your x values, right? And outputs are usually your y values. So your domain here is -2, 3, 4, and 7. Looking good so far because none of the x values repeat. And for the y's, you have 1, 2, 3, 3. Now, it's okay for the y values to repeat. It's not okay for the x values to repeat. So in this case, there are no repeats for the domain. So that's telling me, yes, this is definitely a function. Also, something I like to mention, if you do have like a repeated y value, you don't need to write it twice. So you just need to write 1, 2, or 3. All right, so looking at D here, looks like we have our x's to be -2, 2, 3, and 2. It looks like we have another repeated x value, so it's not looking so good so far. So in this case, because there are two x values that been, or 2 has been repeated, we need to look at their y values. So in this case, this 2 is connected to 1 and this 2 is connected to 4. So they're different y values, so this is not a function, or no, because, repeated x values again. And like I said before, if these x's are repeated, you don't have to write them twice. So I'm just going to erase the other 2 here. And I think I didn't erase the other 4 last time, so I'm just going to go ahead and erase that for you guys. Oops. So if you have repeated x or y values for the domain and range, you do not have to write it twice. Just one copy of it is fine. Alrighty, so let's get into the example 2 here. So for example 2, we're also going to be determining if y is a function of x. So basically, you're just trying to figure out, is the equation here a function? And to do that, you're going to have to figure out what is the equation going to look like. Basically, you're going to have to graph it in a way. But you don't have to like grab out your calculator or anything unless you really need to. What I try to do is try to figure out what type of graph is it. Is it a quadratic? Is it an absolute value? Or is it square root? Once I know that, I can get an idea of what the picture looks like. and use the vertical line test. So the first thing what I'm going to do, and let me just write some step here, is to solve for y. Second step is to graph and use vertical line test. I'll just abbreviate. So if you need some steps there, there you go. So if I were to solve this equation here and try to get the y by itself, I would have to subtract x squared to both sides, right? And so this would give me y equals 1 minus x squared, because those x squares would cancel. Now, when I look at this equation here, I'm like, that there's an x squared, so I'm going to be drawing a quadratic. And if you remember back in Algebra 2, if you have a negative in front of your x squared, this is going to be a quadratic that is facing downwards. It's a parabola that's facing down, or a frowny face, right? So because I already spotted that this was a x squared, I know that it's a quadratic, and I have a visual idea of what a quadratic looks like. So I can easily just use the vertical line test on it, but I can definitely see that it's going to pass the vertical line because it only hits it in one spot anytime I draw a vertical line. So it passes the vertical line test, so I can say, yes, it is a function. Another one here is this one, and again, you're going to have to solve for y. So I'm going to have to add over x to both sides, so that would cancel. And then I would have y squared equals 1 plus x. But if you have a square, if you know how to get rid of a square, you use a square root to get rid of a square. But one important fact is that when you take a square root, you always have a positive and negative value, so make sure you put the plus and minus outside. And so when I look at this answer here, I'm like, this is a square root function. This reminds me that the picture looks somewhat, if I were to draw this graph, it's going to look like a square root function, which kind of looks like a firecracker. Basically, it like shoots one-sided. And this side would be the positive side. But here's the thing, because there's a negative sign here, it has to shoot also downwards as well. And if you don't trust me, or you don't trust yourself, that's what the graph looks like, you can graph this in Desmos if you like. So in this case here, this is going to fail the vertical line test because it hits it in two spots anytime you draw a vertical line, right? So in this case, this is no, not a function. So that's not a function. This one here, I don't even have to graph this. This has absolute value signs. So this is telling me that this is going to look like a V-shape graph, right? Because these are absolute value functions, and they tend to look like a V-shape. So no matter how you draw them, and actually in this case, because I noticed this is a negative in front of the x, this is not going to be a facing up V, it's going to be a facing down V. So let me redraw that so I can be a little bit more accurate. So it's going to be facing down, but you can see it's going to pass the vertical line test, because if you were to draw a vertical line downwards, notice it only hits it at one spot on the line, right? No matter where you draw the vertical line. So in this case, yes, it is a function. So for our last one here, we have to solve for y here. So let's get rid of the 2x by subtracting it off. So I have to subtract off 2x to both sides. And so then I'm left with 3y equals 4 minus 2x. And then I have to divide off this 3 to get rid of it. So that gets rid of it. Y comes down. So I have 4 over 3 minus 2 over 3. And I'll just put the x on the side. By the way, if you have 2x and they're together, you can just divide the 3 into 2. So you can write it like this. And the reason why I like to write it like this is so that you can see x and you can see it as a slope. So this here is a slope. And this here you can treat it as a y-intercept, right? So if you have this type of structure, y equals mx plus b, so if this is a slope and this is a y-intercept, that means you are drawing a line. So this is going to be a line, and I notice this is a negative slope, so it's going to be going downwards. And so in this case, if I were to use the vertical line test and kind of, check to make sure it only hits one time on the graph, it is, right? It's not going to fail the vertical line test because it's only going to hit one spot on that line. So in this case, yes, it passes the vertical line test, so it is a function. So next we are going to be looking at graphing, and specifically, how do you look at a graph that you've drawn or you've made and determine its domain and range? So typically what you do to make a graph is you can use a table or make a table, kind of like what we've done before. And so I'm just going to pick some numbers that I think would work out easier. So like zeros, 1, 4, maybe like throw in a negative. So if I were to plug in 1 and I take the square root of it, or sorry, plug in 0, take the square root of it, I get 0. If I take the square root of 1, I get 1. Take the square root of 4, I have 2. But if I take the square root of 1, I get an imaginary number, right? So if I were to take the square root of -1, this would give me an imaginary number, is what we've learned in Algebra 2. So let me just plot what we have. So at 0, it's 0. At 1, it's 1. At 4, it's 2. So 4 up 2 would be right there. So when you're looking at a square root function, typically it looks kind of like, well, to me, like a firecracker or like a rocket ship going sideways, So it's like a sideways, like, shooting star is how I think of it. Yeah, I think a shooting star would be a good way to describe a square root function. But you'll notice that it's never drawn on this side or the negative x value side, because when you plug in a negative x value, it makes the equation imaginary, and imaginary numbers don't show up on the graph. So this makes our domain a little bit restricted between 0 to positive infinity, because the x's are representing the domain. So the smallest x value here is 0. The biggest x value, it's shooting to the right, so it's going to positive infinity. So my domain is from 0 to infinity, and we always use parentheses with infinities. And in this case, since it does touch it at 0, we use a bracket. And looks like the range is very similar. So range is y values. So the lowest y value on this graph, if you look, is right here. And that y value is 0. But notice how this shoots to the right, but it also shoots upwards. So it's not going to come down, right? So there's no negative y values here, just positive y values. So it's going to be going upwards to positive infinity as well. And I'm also going to need a bracket since it does touch there at y equals 0, so you can use a bracket here. So square roots, just remember, they don't like negative values. Let's make a little note of that. I feel like some of you guys might forget, so that's an important concept. So square roots don't accept negative x values. Okay, so there are no negative x values in a square root, or no negatives under the root. So this one here with a rational function, it also has a few restrictions. One that comes into mind, so the number that I usually like to plug in is 0, right? Notice if I were to plug in 0 here, this would be 1 over 0. But here's the thing, we've learned before, you can't divide by 0. 0 can never be in the denominator, because if it does, guess what? It's undefined. Let me zoom that in so that way you guys can see this. So if it's undefined, that means it's just not going to appear. So this is one of those graphs that have asymptotes, and I'm going to go ahead and draw those asymptotes here. And this is something that we have gone over, is vertical and horizontal asymptotes in Algebra 2. So I'm going to just give a refresher. So because when x equals 0, right here, is undefined, you have a vertical asymptote. So I'll put vertical asymptote. At x equals 0. You also have an asymptote here at y equals 0, and I'll demonstrate why here once we start plugging in values. So horizontal asymptote at y equals 0. So the reason why you'll see the horizontal asymptote show up is when you start plugging in x values. So I'm going to plug in 1. 1 over 1 is easy. It's just a 1. So that means that we would plot right there. If you were to plot in a 2, you get 1 over 2, which is about 0.5, which would be right here. And if you were to plug in 3, you get 1 over 3, which is like 0.333. Notice how when you plug in x values, the bigger they get, the closer it gets down to a smaller decimal numbers. Well, it turns out when as you start plugging in more and more x values, this thing will get closer and closer to the x-axis here, but never quite touch it. So that's why that horizontal asymptote shows up, because it's this line where it's showing you this imaginary line that the graph wants to get closer and closer to, but never quite touch or cross over. And same thing on the negative side here. So I'm going to erase this part. So what I'll do here is make these numbers here, negatives. And so if I were to plug in negative numbers, I would have 1 over negative 1, which is negative 1. So that means it would go right here. If I were to plug in negative 2, I would get negative 0.5, which would be right about here. And if I were to plug in negative 3, I get negative 0.333. So also creating that asymptote towards that y equals 0 line, or that x-axis. So again, you're going to have that asymptotic in the way, so that way it is gliding across that asymptote but not quite touching it. And so now we can figure out our domain. So our domain is representing the x values, and you want to start with the left side, and I noticed that it's pointing with an arrow to the left, so it's going to negative infinity. And as you trace it, notice that it's heading towards the towards 0, but it can't cross 0. So it goes towards it, so I'll put 0 here, but doesn't cross it. So that means that I have to use a parentheses on 0 because it can't touch it. You would use a bracket if you can actually touch 0. So this is one section of the domain. After that, it goes from 0 to positive infinity because it's pointing to the right in the positive direction. So it's going from 0 to positive infinity. And so it's like this part here is part of the domain, and then this part here is also another part of the domain. It's going from 0 to infinity. So you have two sets of domains, so you want to use a union or a U to show that they are together. As for the range, it's going to be very similar. So now you want to look up and down. So starting with the negative y values, it's pointing down with an arrow for the blue curve here. So it's because it's pointing down, it's going to negative infinity. Then it goes back up towards the y equals 0, right? So this is heading towards y equals 0. So it's going from negative infinity to 0. Again, I have to use parentheses because you can't actually touch y equals 0 or this line because it's an asymptote. But then after that, it goes from y equals 0 to positive infinity, so it is pointing upwards. And again, you have two sets, so I'm going to need a U to show that they are together. And that's it for the rational function. So like I said before, this one here is a little bit strange because one thing you'll need to remember is that with rational functions, let me put this up here. So rational functions, you cannot divide by 0. Because if you do, you get something undefined. So that's something important with rational functions. And then I think I mentioned in the other one for square roots that you can't have square roots that have negative values. So those are the two things you'll need to know about square roots and rational functions. All right, let's get into example 4, our last example here. So for this part here, we have a example where you are finding the domain. So domain, like before, we're just grabbing those x values if we have coordinates. So I'm just going to grab those x values and put them in a bracket or in what we call a set. And that will help us show the domain. So all it wants here is a domain. And there we go, we're done. And you can also tell it's a function too because all the x values are different. And then this next one here, you can go ahead and graph, but I want to teach you guys to be able to look at a function and tell if what its domain is based on the type of function. So when I'm looking at this here, I notice the highest power, and you always look at the highest power if you can, is 2. Anytime something is 2, that tells me that this here is a quadratic. And I know visually a quadratic looks like a U or upside down U. So in this case, this is a -3 in front of the x squared. If it's a negative coefficient out here, I know it's an upside down U. Not that it makes a huge difference, but it's nice to know what it looks like. So because it is a parabola, the nice part about parabolas is that they always stretch left and they always stretch right. If they're stretching left and right with an arrow, it's going from -infinity to +infinity for its domain. In other words, when you have a domain that's going from -infinity to +infinity, you have something called all real numbers. So here's the thing. Because this is a quadratic, the domain will always be all real numbers. And that's it. So anytime you notice that something has an x squared in it, or the highest power is x squared, it's a quadratic. End of story. Domain is all real numbers. All right, this one here is a rational function. The thing you need to know about rational functions, like I said before, is they cannot divide by 0. That's the only x values that affect it. Okay, so in this case, this denominator here, it can't be 0. So in this case, what I'm going to do to figure out what number causes it to be 0 is pretty easy. All I do is take the denominator and I set it equal to 0. And so I'm going to put a slash through this equal sign because in this case, I don't want this x to cause this equation to be 0. So I just need to figure out what x can this function not be. So to solve for this, it's like, any other equation that you've ever solved. You'll just try to get the x by itself by subtracting over 5 in this case. So x cannot equal -5, which makes sense. If x was -5 and you add it with a +5, it's going to make it 0. So in this case, you don't want that x being a -5. And that's it. So it basically says that this equation works for any x value except when x equals -5 is what it's saying here. And then this one here is a square root. Like we said before, square roots can't tolerate negative numbers underneath. So I'm just going to write a little note. Cannot have negative square root. So what you have to do is take the inside here, so 4 minus 3x, and set it equal to 0, but you want to say that it has to be greater than or equal to 0. So here's the thing. Inside this root, if it was a 0 inside this root, it's fine. The square root of 0 is 0. Has no issues. And if you plug in a positive number, has no issues underneath a square root because a square root of a positive number has an answer. But if this becomes a negative value, then we're in trouble. So what we do is we set the equation greater than or equal to 0. Because as long as this whole value is either positive or bigger than 0, it is okay. So then you solve it like a regular equation. Like you can add 3x to both sides. So that would cancel. 4 would come down. This would be a 3x over here. You can divide by 3. That would cancel. And so this would be 4 over 3. Essentially, what this is saying is that as long as x is less than or equal to 4 over 3, then this equation won't give you imaginary numbers. So in this case, our domain is restricted by this condition, that x has to be less than or equal to 4 over 3. All right, and that's it for domain and ranges and vertical line test.